All right, good afternoon. Today I have put some things in notes for Module 12. And if you click through, you should see Module 12, where I have some notes on advanced summer design. They're pretty extensive, and so it was kind of hard to convert over, but you should be able to see that, right? I also have a link to student success notes. And so I'm just going to jump right into the exam, which I've been able to do 20 so far. So I'm hoping to have it all completed by class time next Wednesday. All right. So first, I'm just going to mention some things. Then I'll go over issues because almost every exam was different. Okay. So I'll just kind of go over issues. But there was something that I thought was interesting is that a lot of people were scoring close to 100% on the homework, but not so much on the midterm. And if anybody wants to shed some light on that with me privately, that'd be great. I thought that a nice extra credit exercise would be I was just checking to see if I was recording, would be to redo your exam, right? But now you've gotten some, or once you get some feedback, right? Once I make it available, right? Check your work with LT Spice or Python or Desmos. And so then return it into me. But this will be during an office hour appointment. So it'll be kind of an ongoing project, if you will, right? Because I want to talk to you about it during office hours, right? Just in case to you get stuck, you've gotten stuck on something. All right. So that'd be one thing. Another 50 points extra credit is to create a good study guide for midterm 1. Now, if you've created a study guide and you did well, then all you have to do is turn it in. But if you are thinking now your study guide needed improvement, well, create the study guide you wished you had created, right? Because it'll be good for the final exam, right? I'll make that a Canvas assignment, all right? But really, you should have a copy of your questions. I know some of you didn't or got a little bit confused or something. But the thing is you can start now studying for the final exam for this. And even if you did well, you kind of need to review. Now, just something to be said. Midterm 1 grade can be okay. There will be similar questions on the final exam from midterm 1. All right. And so if you do well on the final, well, then it can wipe out whatever grade you got on the midterm. All right. Sometimes 110 hits people a little hard, but you actually learn it by the end of the semester. All right. So the thing is there's no albatross around your neck. There's no anchor around your neck. You can still get the grade you want to get, right? We just might have to tweak what you're doing. You might be spending enough time, but you just might not be spending it the right way. All right. Again, office hours for which you get extra credit is a great way to get some customized instruction on what to do. Okay.
Professor?
Oh, hold on, there's a question. So what are the extra credit points going towards to? It goes towards your homework, just like all other extra credit. Well, I don't know who asked the next question, so just ask it again, please.
I was gonna ask, can we do both of those, or do we only get to pick one?
Oh, do both.
Oh, okay. Okay.
Yeah, but only one each, right? Right. And you know what? Let's just say, let's get cracking. And I have to talk to Professor Panay about when midterm 2 is. Okay. So there we go. There's even more. And while we're here, because I know I say things and I know sometimes we're not all quite ready to receive whatever I happen to be saying. You can earn extra credit for coming to office hours. Now, asking a profound or interesting question, that's usually like an email. Identifying any typos. You can do poetry or haikus about 110 topics. You can index a lecture video, and somehow if you show some documentation that you've helped with someone else with 110. Now, yeah, this has to come in so I can process it before the final exam, right? It can't be the grades are out and now you're looking for extra credit. But that's like a big question I get at the end of the semester. Is there anything I can do? Right? Well, here's things you can do. Sorry, I don't know who asked the question. It didn't pop up, but did that answer your question, whoever that was?
Oh, thank you. If you're talking about the extra credit,
Yeah,
yes.
yeah. Okay. So, like, way back when, right, I had tried to start in on a study guide, right? Because open book, open note exams can kind of catch you by surprise. And so this was actually my study guide. A good thing is that there's this particular pitfall that I won't go into, and I didn't really see it this time. Now, unfortunately, I did see new pitfalls, but again, this was just one day, right? And um, we can totally do what we want to do. All right, there's no reason to quit. There's since there's no curve, you can help one another and not get penalized, if you will, right? Because what would happen to me is I would help other people learn the material and then I would flub the exam sometimes. All right. So for question 1, we had to do a describe a signal. And so here's like a Desmos plot, where here's a step, here's a ramp, all defined, and then you just go through. Now the thing is I felt that a lot of people might not have been checking their work, because if you'd actually done that, you could see that the shapes weren't lining up. Now, that link right there goes to this plot that I'm showing you. Okay. And to me, a good take-home study guide, right, would be a link to all the software that you would use to check your work during an exam. And now, yeah, I'm doing it in Google Docs, and maybe you'd rather do a by hand thing, but like whenever I have a plot, now these plots I happen to have done in Python. You don't have to do that, but the point being is that you seems a little slow today. Anyway, every plot is linked to either the Python code or the LT Spice code that created it. Because I find that I've created so much code, I don't even know what it's called anymore. But if I'm going through my op amp section, oh, all right, I know what that is. And then I can go find the code much more easily. All right. So that's just some ideas. All right. Now, what tended to happen was that the slope factors were, if there was a mistake, it tended to be in the slope factors. All right. And usually on the ramping parts where, this slope here or that slope here was wrong. Usually the step jumps were correct, right? And the time delays were in general all correct. All right. But sometimes there would be some missing things. All right. Some just wrote it out and either it was right or it was wrong. They didn't go through and kind of show their work. And the people who are kind of, what they'll do is they'll circle this and say UT and then going down, and then they'll have a circle here going, how to flatten it, how to jump, and each point will have a little note. Okay. And it seemed that the people with the best documentation were doing better. Okay. Now I don't know. But any questions on question 1? Okay. Question 2.
Sorry, yeah, I had a question. I was just muted.
Yeah, shoot.
If only one of the slopes was incorrect towards the end, do we get partial credit or is it just incorrect?
So the scheme is, I don't know if I found anybody with just one slope wrong. It'll be 2 slopes wrong, and that'll be like half off.
Half off. Oh yeah, sorry, it would
Okay.
be 2 slopes because you have to
But
cancel
then,
it. Okay.
but then, so the thing is yeah, let's say there's 5 terms. You could say 2 points per term, but at some point, then it gets really off. So any more than 2 errors, it's like 0.
That's fair.
Because then
That's fair.
it kind of demonstrates a kind of a lack of knowing what you're doing. Okay. But yeah, that's a
fair.
great
Thanks.
question. Yeah. Thank you for asking. Anything else? All right. So for question 2,
I have a quick question.
Yeah,
It's not related to the exam, but it goes like this. How do you exactly calculate a phase shift between the two different sinusoids?
Justin, was it?
Yes.
Justin,
Sure. Actually, I'm okay. Fine.
sorry, somebody's talking over the channel. That wasn't really on the exam. So if I have time, I'll come back to it, right?
Okay.
But and certainly at the end of class, if you want to stay out, I can answer that. Okay. But right now
I
I
can do
gotta
that.
stick to topic.
Yeah,
Okay.
yeah. Okay, I can do
Okay.
that.
All right. So really there was kind of two. Now it might not have been shown omega naught squared, right? So actually, I'm just going to cross that out and just call it A times B. And then the gain could have been 1 or 10 or 100, right? And A and B could have been, A could have equaled B. A could be like 100 times B. And I think A could be 1,000 times B. And that's pretty much the algorithm, if you will. So for the magnitude, right? And yeah, by now, I know what a second order high pass filter looks like, right? So I'm not going to go over the derivation, but just a rough sketch, right? That would be 20 log gain. That would be B. Well, I'll call that B. And I'll call that A because I said A was 100 times B equal, right? So here's two, different things. And that would be, let's just give these conditions 1, 2, and 3. This plot would be good for 2 and 3. The only thing that you would need to add is 40 dB per decade slope, and then it goes down to 20 dB per decade slope, right? The other condition I'm going to actually just draw it in a different color. Right. The gain would be the same, but there'd only be one breakpoint, and it would be 40 dB per decade. All right. Now the phase it's going to go from 180 down to 0, passing through 90. And there'll be one, and it'll all happen at A for A equal to B. All right. But if A equals like 100 times B, Okay. So if A is 100 times B, that's 10. And so A would be here, right? Which means that A divided by 10 and B times 10 are in fact the same point. Okay. And what you get is you get this same shape, 180 to 0, right? Now that but here you get B divided by 10, and here you get A times 10. All right. And then it just passes through this point, which is neither A nor B. Okay. This is B times 10, which would equal A divided by 10. But there's just one break and it's just spread out, right? So you would get, something very similar, except it would spread it out. Now, when A equals like 1,000 times B, what happens to the phase is you get the first pole that goes from 90 down, 180, down to 90. Then the next pole kicks in, and that goes all the way back down to 0. And this point would be A, and that point would be B. So it spreads out. All right. So the magnitude and phase are graded independently. One mistake that I saw is, I'm going to just try to draw this by hand, is that it looks like they're trying to draw the Bodie plot that LT Spice would give you. But this is the asymptotic Bodie plot. And so when you draw it like this, I can't tell if you know to do the divided by 10 or times 10, right? Oh, sure, I can see 180 down to 0, right? But and then two, there was this issue with phase. And again, I've only done 20, but like the phase will do this. I'm not quite sure. You would really have it something like that, right? And so if we look at the algorithm, okay, for phase, right, it's really like ramp functions, but instead of time, it's ramp like omega knots. So it's really like ramp omega minus omega naught. And of course, you have to make sure everything is on a log scale and things like that. But right, what that would be is if this would break up at omega naught, and then if I multiplied it by 20, then I'd get my 20 dB. And in fact, I wrote a MATLAB program. I have my UT, my RTs. I can enter in the poles, the zeros. Let's call it the break frequencies, not the poles and zeros themselves. The gain. And it goes through, and you can see that I'm, 20 times T or ramp T's, right? With poles, it's minus 20, right? Then I converted it to a function to evaluate. and out pops a rather difficult asymptotic Bodie plot. All right. So let me go back to my notes. Sometimes, yeah, if the breakpoint is supposed to be 30, it should say 30, but it would say a different number. In Mom, it was very hard to get 30, but I could tell if you were trying, right? But it would just be something really off, right? And that's magnitude. Sometimes on the phase, people would do this for the phase. Well, I can't tell. Do you mean magnitude? Is that going on forever? Phase always has to flatten out, regardless of whether this starts at 90 and goes to 0, or 0 and goes to minus 90, or 180. You have to show everything extended, right? And I think sometimes other things are, I don't like to characterize people as being lost, but people would put a slope up or a slope down as if maybe they ran out of time. Okay. I don't know. Of course, sometimes, yeah, sometimes the gain wasn't correct. Oh, this is wrong. I'll come back. All right. So, I mean, in office hours, if yeah, we can go over your own particular thing, right? But by now, that last video really just shows you how to draw it, not necessarily where anything comes from. But bearing that in mind, are there any questions on question 2?
I have a question, Professor.
Okay, Fernando.
So here's my question. So I'm slightly confused on, for example, a second low pass filter pulls you from 0 to 180 degrees, correct? So my question is, when you have critical frequencies, let's say at 10 and at 10K, you know how on the phase plot, you're supposed to show a decibel or a decade before and after, and then at the end flatten out. How do you stretch that middle point? Like, the 45 degrees on the left, 45 degrees on the right, without going over the 180 degrees.
Well,
Like if you
guess,
have
you can stretch all you want. I guess I'm not getting why I would be forced to go over 180 degrees. So here's the thing. Let's just take so there's 2 poles here, right? So we have 2 break frequencies. And so what frequencies do I want to plot? Well, I want to have to plot 10, and then I'm going to want to plot 1. But to extend it, I have to plot 0.1. And then on the other side, I have to plot 100, but that doesn't show the extension, so I have to plot a K. Now, here I am at a K. Oh, I've already got it. I've already got 1/10 of it, and I've already got 100th of it. And so now I just need to extend it, right? And then I'm just going to put break frequency 10 and break frequency 100. Now this is a low pass filter, so I know it's going to be 0, 0, 10, right? So 10, 0, minus 45, minus 90, and then it continues being minus 90. Remember, the phase shape, flat, angle down, what? All right, there are things that can make it go up. If you had S minus A, right, it does make the phase, but we're not doing that. Everything's on the left-hand plane. So every shape, wherever it starts and ends, it's flat, down, flat. Now with the 1K, right, 0, 0, 0. So it's still 0 at 100K, at a tenth, right? Then minus 45, then 90, and then it stays 90. So now I'm flat until 1, and then I'm minus 45 at 10. Wait, yeah. Then at 100, I'm minus 90. Then at 1K, I'm minus 135. And then at 10K, I'm minus 180, at which point it flattens, okay? And if these were farther apart, and I'm just gonna, randomly draw something farther apart, right? I would have a break frequency, then it would flatten at some point, right? And then if they were equal, and it would happen, there would only be one pole if they were equal. So it'd be a tenth to 100 times. Okay.
Okay, thank you. I wasn't aware about that flattening out part in the middle because, like I said, I was like, it's too far of a gap. And if I kept on going 45, 45, or 90, I would have passed the 180 phase. So that's where I was a little.
Well, yeah, I mean, the thing is, well, like I said, you have a chance to do it again. But the thing is there's even keeping things to practical plots, like real things, right? Not just made up, like, I mean, maybe this system exists, right? But I was really just making it up, right? That to me is somewhat of a random problem that I wouldn't show on an exam. I want things that'll come up on a job interview or something, right? So you have high and low pass filters with real poles. They can be repeated, separate, and far apart. And if you follow this technique, you should have gotten it. But I can imagine that you didn't know you were going to get it. Like you intuitively didn't realize that's what the shape should be. Okay, I get that. Anything else? Oh, sorry.
No, thank you. Appreciate it.
Okay, Fernando, thank you. Okay, now number 3. Pretty confused about number 3. It's been on almost every midterm I've given since I started teaching this. It's on the practice exam, right? I believe I derived it several times. I believe I said it was going to be on the exam several times, and I said it would be an interview question most likely several times. So I'll just go through it, but I am at a bit of a loss as to what's going on here. Okay. So one thing though was omega naught was not calculated properly, right? Where I think maybe what's going on is you have 1 over RC equals omega naught. And let's say it should have equaled 100. Sometimes people were putting like 0.01 or something, but sometimes it's something I couldn't even figure out, right? I'm trying to get everybody's thing graded right away. So you can come see me as to why that should be, but really it's just 1 over RC, or maybe people were doing R over C. I couldn't quite figure it out. All right. But that was an error. Used what I call a long way to derive it. All right. Which then led to problems. So like to me, just do it as simple. I assume an ideal op amp, and that gain is 1 plus the R on the feedback and the 1 connected to ground. Maybe the numbers are different. That's why I put that there. Then I use voltage division for RC, right? With impedance. There you go. Then I just multiply them together, right? And like I said, 1 over RC seemed to give some folks a problem. Okay. Same thing for the high pass. Assume it's ideal. It's that. It's high. Use voltage division and you get the voltage, the high pass, right? And yeah, when I look at that, if I let omega go to 0, this is going to go to 0. If I let it go to infinity, it's going to go to some constant. So the Bode plot's going to start low and end flat. Here, it's going to start flat and end going downwards, right? With the magnitude, well, the thing is, if the transfer function was wrong, it was going to be pretty hard for anything else to be right, okay? But sometimes it'd just be missing. And I would look in both places, all right? I know I said to do everything on a piece of paper, but if it was in mom, I looked at it. And if it was mom, and I could tell mom didn't grade it correctly, right? Because it's a hand sketch, I went and fixed it, right? Time domain step response. Many times the time constant wasn't right, or it just seemed there's either a confusion between the step response and the impulse response, or a confusion between the high and the low. Okay. And then the plotting of the step response, probably not really showing it going in the 5 tau. You got to label that 5 tau, right? And what the maximum voltage is. Or maybe it was just switching the low and the high, reversing it, right? Or missing it. It could be, maybe a lot of people were running out of time, and we can talk about that for office hours. All right. I'll take a question on this, but I do have so much documentation on this that I might not answer, but don't hesitate to ask. Don't be afraid to ask. Okay. So for number 4, that's where you were given 2 functions and you had to find the convolution. You could do it any which way you wanted. The equation, more often than not, is correct. So everybody understands that process, right? But the filter type was most often the most incorrect thing. And because it's a first order, it can't be notch or band, right? So there might have been 4 choices, but it really only could have been 2. And I didn't put it in there to trick anybody. It's just I wrote that question a long time ago. And sometimes when I go edit a question, I make it worse and put in a bug. Okay. But let's just have a quick review. A low pass, right? So this is a step response. I mean, this is a step input, right? It's got an edge. It's got some corners, right? A low pass will pass DC, right? So it's 0, and then it's going to pass some DC, and then it's going to kind of round these edges, right? Now, it could round the edges like this, all right? There's one where it goes like this, but it's 0 and it flattens out, right? And it's rounding those edges, all right? There's an edge, and a high pass filter will detect that edge, right? So high pass filters immediately change, right? But they're blocking the DC, so they go back to 0. They could go back to 0 like this. They could kind of go like this or exponentially down, but they start and end at 0. Okay. It's true, band passes in the frequency domain look like this. Okay. But a band pass in the time domain, we actually get into that at the end of the semester, but they can be difficult to interpret. All right. And a notch, right, does this in the frequency domain, right? But in the time domain, it does this kind of weird thing. You see the high pass and the low pass because it's blocking out the middle. All right. But maybe what's happening is people look at this and just put omega and say, oh, it's a band. Or maybe when it does this, maybe that's it. If they see that, they call it a band because it went up and came down, thinking that was omega, but it's time, not omega. And then here, right, it goes down and comes up. Maybe they're thinking notch, but this is time. Okay. It detects an edge and then goes back to 0. All right. Again, sometimes you might have gotten things right, but then didn't plot it properly. And I was trying to say that here. Simple. I had it sample question too, but I had scale and delay. What are the basic functions? And then have sample plots that show you what to do. Okay. And I even had a suggestion to check your answer. All right. Any questions? Rayad, is too soon to give an average. Okay. I've only done 20. But the truth of it is, it doesn't really matter what the average is. There's things in this class that you have to know for your career, and the department has tasked me to, you know, teach it to you and then check whether you know it or not. Okay. I'm not trying to be harsh or anything, but if you look at the technical electives, 110 kind of is needed for almost half the curriculum. Okay. Everything but the digital. Okay. So for question 5, right? You had to the input was something like this. I'm just going to take a break and answer a question. By what date should we look to turn in the extra credit for the study guide or the redo of the midterm? So, I understand that you have other classes, right? So, but I'm going to give you the answer of you should have this done, right, by the end of the weekend. Okay. Now, of course, I know you might have other exams and you have to work it in and you didn't expect to do this assignment. But the reason why I would want you to do it right away is that it's fresh in your mind right now. And that if you have it done now, right, that'll be more time in your head that you will have known it before the final exam. And now I'm going to tell you a karate story. I'll try to keep it short. But we have these tournaments where you have to, you know, do these maneuvers, right? Sometimes you make up your own, what you would call it, a fighting form, right? Where you're pretending to fight an invisible opponent, right? So sometimes you are told to create your own, use a weapon, don't use a weapon. Sometimes you have to do some specified form. And what I found is that like a week before the tournament, however I do that Sunday is how I will do on the tournament. And that any practice that week of the tournament is more keeping in shape and not forgetting anything. And sometimes what we would do is have these practice sections on Wednesday night, and people would give you advice. Oh, you should do this. And then I would try to follow the advice and usually screw everything up trying to follow some last minute of advice. And so now, yeah, if I know there's a tournament coming, I think there'll be one in April, right? As soon as I get the task, I start practicing really hard right away. And then actually my practicing, like the week before, I hardly do anything. All right. Now I know you have more than just one form to learn for karate, and it's different, but really the sooner you learn something, the more time it has to stay in your head. And so, yeah, when people say, when should I start studying for the exam? Probably, you know, the second week of class, right? But now, well, I think I monologued enough. I have another question. Is it okay to go over personal exam questions after class? I really think that'd be better for office hours because it is private. And sometimes I forget to turn off the recording. Okay, Ellie? Eli? Okay. Remember, that extra, I just feel like I try to get people to subscribe to my YouTube channel, saying that there'll be extra credit for office hours. All right, so back to this question. Well, if you look at it, really, almost all you need to know is right here, the step. Oh, sure, there's this, right, where there's a slope, right? And so, in a way, you could almost answer this question just off of this, right? And that there'll be two low-pass filters. Oops. Okay. And what I'm trying to draw is that it's going up so quickly, right? This one is going a lot faster than that one, right? And then for the high pass, now they're all going to the same point, 1, right? So one is taking a long time to decay, and the other one is taking a short time to decay. All right. So that there is, and all we need is the magnitude here, right? We have two magnitudes, right? This omega 2 is a lot bigger than that omega 1. So its time constant is a lot smaller. So it's the, oops, my bad. So it's the one that rises up quickly, right? This one's time constant is smaller than that. So it's going to take longer to charge up. Here, so, this one actually lets in more DC. No, blocks more DC and lets in more high frequencies. This one blocks DC more, but really, here's the time constant. This omega is bigger than this omega breakpoint. So this time constant is smaller than this time constant. So this is the one that decays quickly, and this is the one that decays slowly. I think I made sure I didn't turn sticky keys on, Andrew. I almost did. Okay. But anyway, so really that's how I would get the right answer. And you have to say, oh, this omega is bigger than that. Thus the time constant is bigger or smaller, right? Thus it decays smaller or faster, right? And then, yeah, what makes this a high pass filter? Because it's filtering the low frequencies and passing the high. What makes this low? It's passing the low frequencies and attenuating the high, right? Now, yeah, what makes this a low pass? It's rounding the corners and passing DC. What makes this high pass? It immediately changes on the edge, and then it decays back down to 0. Right? So those kind of comments, right? Really, it's sometimes people would say, well, it's a high pass filter with no, the reason why it's a high pass is because it's a high pass. It doesn't quite work, right? Is it a low or high, right? And so now you're looking at the Bodie plot, right? And you got to say Bodie plot passes high or low frequencies, right? Transient detects edges or passes DC. And then how fast? This one has a time constant roughly of this. This one has a time constant roughly 100 times bigger, right? And that would be a full justification. All right. I need to talk about advanced summers, but I got time for a quick question.
So I have a quick question.
I can't quite hear you.
Yeah, when you have a big value like how to use a Desmond to check your work when you have a big value like 100, 300, or 1,000 stuff. It's kind of hard to see the shape in using Desmond when you have a big value.
Um, so, A is equal to 1 there, right? So now you can barely see that, right? And so if you come, sorry, my thing is right in the way. Where is it? Settings. I guess that's how I do it. Now this here isn't real. That's because I'm using tanh to get a smoother curve, but it's really sine t. But what'll happen is you won't see a solid line. It'll kind of fade in and out, but it'll be more accurate. Okay. You see how it's purple or blue, and then it comes down here and then kind of disappears. That's just what it does. It doesn't plot a line through each point. Like it's saying that's a discontinuity, which it is, right? But sometimes it's hard to follow. Now, that being said, right, with these problems, right, well, that's how you check it. I'll leave it at that. Okay. Does that answer your question?
Yeah, thank you.
Okay. So let's start. Now, these notes, there's a link in Canvas and from the Google Docs. And rather than redraw some things, I'm just going to kind of lead you through these notes. Okay. Devin, what I'm doing with the grading is your grade will be in two places. So where you uploaded it, I'll enter in the grade, but I'm also having in mom, I'm typing in the partial credit or the full credit or whatever, and then saving it. So it should pop up also in your in Canvas where it just says midterm 1 mom. It should be there, right? So it'll both grades will be the same eventually. But it's something that you can check. Okay, Devin, did that answer your question? Okay, great. So we're going to use something called an advanced summer structure. And the whole point is that you don't need all these extra op amps to do addition and subtraction. All right. And the book uses this kind of inefficient way of doing it. So the book kind of does this inverting summer routine here. And we'll call that RF and RB and RA, where V out equals minus RF, RA, VA minus RF, RB, VB, right? Because it's just kind of easy to derive. And it does have some advantages. Sometimes when something's easy to derive, it's actually a good way of doing something because it's simpler, right? Now, if I want to, what if I wanted to add these together? Well, then I'd have to put another inverting op amp, and then I could invert it. And then if I wanted to have one positive and one negative, I'd have to keep mixing. But no matter what, I would use nothing but inverting summers. So, which needs two op amps. All right. Ultimately, we're going to use an op amp with this kind of structure. Where this can be, what I've read is you can have 4 inputs on each side before it gets a little hard to deal with. Not mathematically, but I think I'm laying it out on the board. So I can have any number of, I can have an arbitrary number of inverting inputs. I can have an arbitrary number of non-inverting inputs, right? And then there's a trick, is that if I replace this with a capacitor, right, I can actually integrate the sum of these values, all right? And so it's just a highly efficient way of using an op amp, all right? And when we're going to use this structure in a filter later, right. So just to clear up some confusion in the chat, while mom was used just to deliver the test, I'll be entering your grades in both places, regardless of where you did it. If there's a way for me to give you points, I will do it. All right. Now I'm suggesting you should have all of these things done by the weekend. But if you can't, all right, turn it in later. All right. But to take it to the extreme, to turn it in the night before the exam won't do much good. For an integrator. So basically I would have 1 over, well, if all the R's were the same, if I made all these resistances the same, it'd be 1 over RC minus V1 minus V2. If this was V1, V2, V3, V4, right? So I can add and subtract everything I need to, and then integrate it. It's just extra credit, Andrew. Yep. You know what? And I actually put it in today's notes. Okay. Whether the yeah, I mean, it's extra credit. All right. So that's, this is a very efficient structure. I can't print it out for you any longer, right? You just, if you're missing a question or something, you were supposed to print it out, right? So, if it's one of those, just do it from the practice exam if you don't have it. All right. But I cannot be, honestly, I'm sorry. I'm not annoyed. I just don't have the bandwidth to be printing out your old exams. All right. Okay. So here's an op amp, and this is the feedback transistor, because sometimes you just run out of numbers, right? R1, RA, I3. That's the feedback. It's the negative feedback transistor. That's why I call it. And then the thing is these op amps will be driving other op amp resistively loaded circuits. And something you might not know is that you need to have at least a minimum of 2 kilo ohms driving it. Now, usually we just leave it empty. Well, you're driving infinite ohms, so it's okay. But an op amp to drive 1 ohm or 20 ohms or even 100, it can't supply the current. All right. You want to see your exam, just make an office hour appointment. Then we can figure that out. Okay. That should be no problem. Okay. So that's just a heads up. So the thing is there is this kind of advanced structure, which would be very difficult to try to derive it out. Here's the proof. So that's 1, 2, 3, 4. So that's 4 pages of proof. Okay. What I suspect is that an engineer was looking at it and noticed, oh, I think this will work. And then it did. and then they proved themselves that it worked, but they didn't. I think probably there was a moment of inspiration that then they proved with an equation, but trying to derive this with it's a bit difficult to prove this relationship I'm about to tell you. You could find out what it is, right? Just use superposition and all of that, but it'll get quite involved. Okay. But this is the basic structure. You're going to have some inputs on the inverting side. You're going to have some inputs on the non-inverting side, right? And then you're going to have this RF resistor. And it's going to be, the reason why I call it RF, even though this isn't feedback, is because it needs to be the same, right? And I've used 100 kilo ohms because that'll minimize the current flow. And sometimes when things are in, you might not realize when you're driving a load that there are things that could be in parallel that will make the effective resistance smaller. All right. So there's nothing magical about 100K. It's just I've done a lot of problems where if I start off with 10K, ultimately I end up driving loads that are less than 2 kilo ohms and I have to start over. And so it seems 100K is pretty good. If it's too big, there's other issues as well. All right. So in order to use the advanced summer equations, you have to have some rules. All right. And so we have to have the sum of these gains equal the sum of these gains. All right. So, I mean, these ones are easy to see because it's an inverting summer. So since everything is 100, right, this is -1 gain, -2 gain. That's a -1 gain. That's a -1 gain, right? And so the total gain on that side would be a -3. So for this to work, I have to have a +3 gain, right? Because the way this structure works is that it'll be the gain on V4 will be 100 divided by 100 here, 100 divided by 100 here, because it balances out that non-inverting summer 1 plus those resistors. So that's the sum of the gains, right? 1, 2, 3, and that has to equal 0. Okay. But rather than try to like, oh, well, I don't have enough gain here, let me try to adjust this resistor smaller to balance that. Well, now that won't work because you've just, what if you really wanted a gain of 1 on 4 and on V5, right? So that won't work. You could, but now you're not getting the equation you want. So rather than do that, you add a dummy resistor. So what I would do is if I added another 100K resistor and tied one end to ground, that's like a 6th input, but since it's tied to ground, it's set to 0. And so what it'll do is that'll give me a -3 gain here, and it'll give me a +3 gain here, even though one of the inputs is going to 0, right? And so it'll balance and thus it'll work. So that's kind of an overview. So let's just go through the details of that example. So this is the equation I want, right? I'm designing. I'm not analyzing. I'm going to design and then analyze, right? So I want -1 times this, -1 times that, -1 times this, +1 times V4, and +1 times V5. So let me sum the gains, right? And it turns out that I'm missing like a gain. So if I say, what's my GD? That gain will be 1. That means I need to add a dummy signal with a gain of 1 to the non-inverting side. Now here's the equations, right? R1 will be equal to RF divided by the absolute value of the gain 1. That's 100K. And you can see that because it's 1, everything turns into 100K. But then I have this dummy resistor I have to add as well. And because I only needed 1 more unit of gain, well, then RD will be 100. And so here, right, everything's 100. This one, that input is just tied to 0, and that will give me this gain. All right. Now, what if I wanted something a little more complicated? Minus 10 times V1, minus 20 V2, and then I have a 30 gain and a 40 gain. Okay. I just sum everything up, right? I want that to equal to 0. But in this case, my gain of my dummy, I'm missing 40 on the negative side, right? Because I have 30 plus 40, that's 70. Plus 70, this gives me minus 30. I need another minus 40 to balance it out. Okay. So I have each of these gains where gain 1 should be 10. So RF divided by the absolute value of negative 10 gives me 10K. The other value gives me 5K. The feedbacks, R3 is the non-inverting 3.3, R4 gives me 2.5. And then that dummy, I needed another 40, right? I needed a negative 40 on this side, right? And so then here would be the final structure. RFs are the same, right? That was V1, V2. I add the dummy. So this gives me minus 10. This gives me minus 20. This one gives me minus 40. And then this is 30 plus 40 gives me 70. So the gains balance. Here's another example. I have the gains on the inverting side are still the same, minus 10, minus 20. But now I have 5 and 25. Sum the gains. And it looks like I don't need a dummy, okay? Because minus 30 plus 30 equals 0. So actually I don't need anything, right? And so this gives me each resistance. And here, notice that if RF wasn't large enough, then I might be going below 2K, right? And so then this would be the structure. The proof makes interesting reading. And that's really all we have time for today. Okay. Now I know some people have questions. I'm going to turn off the recording. You got to go to 112, then you got to go to 112.
See you Wednesday.
See you Wednesday. Meeting control.